All right, now we're going to talk about equilibrium. Now, equilibrium is important to understand because virtually everything in chemistry, virtually every chemical reaction, occurs by random molecular motion. What that means is that the particles are, just bouncing around randomly, bouncing off the walls, off of the container, bouncing off of each other. And in order for chemicals to react, they need to bounce and into each other and collide with one another, come into contact in order to react. And that happens randomly through random molecular motion. Another important thing to note is that most reactions don't just go one way. Like usually you might see a reaction written out on the board going one direction, this plus this equals some compound, but in truth, most reactions have a backwards reaction also. It can reverse itself and just continue to go back and forth at some fixed rate depending on the concentration. So, for example, let's just take a look at these. Let's talk about equilibrium in a different sense, not necessarily in a chemical reaction just yet. Here I have a container. There's two rooms separated by a divider here, but there's a hole in the divider. And there's an equal amount of particles on both sides, and imagine them bouncing around randomly. You can imagine then that some of the particles on the left side are going to go through the gap and enter the right side of the container. Now, it never really gets lopsided because, well, the guys on the right chamber are bouncing around also, and they're also have an equal chance of bouncing into the left chamber through the gap. And so we say it's at equilibrium in that it's equal. They're never off balance because they have an equal amount of an equal chance to go back and forth through the gap. And so, yeah, at any given instance, there might be an imbalance, but in the long run, in the big picture, it's pretty much equal throughout. So this is at equilibrium. Now, how I can disturb that equilibrium is, say, I add more particles to one side. So in this picture, I've added way, way, way more particles onto the left chamber. Now, what do you expect to see in terms of the rates of particles going from the left to the right and from the right to the left? Well, on the right side of the chamber, it's the same amount of particles as in the first picture, so we can say, it's still going to the left at the same rate. But now that I've added so much more particles on the left side, and they're still bouncing around randomly because there's so many more particles, it has an even greater chance of going from the left to the right. So there's a huge, huge movement from left to right because there's so many more particles on the left chamber. And so if I add more to the left, it's going to push the rate to the right, and it's going to do this until they equalize and the rates balance out. Because if you can imagine more particles going from the left to the right, well, the left side starts decreasing and the right side starts increasing in particles. And so this rate will slow down, the top one, and then the bottom one will start to speed up until they equal out again and they reach what we call equilibrium. The rates of going back and forth are the same. Another way I can disturb the equilibrium is, say, I remove some of the particles. So I removed a lot of particles from the left side here, and so and on the right side there's still the same amount of particles as in the other examples. So you can imagine the rate is about the same as when we first drew it. Now for the rate going left to right, however, since there's so few particles on this left side, it's going to be less often that one of these particles are going to move to the right. So the rate is really small. And again, the rate is going to be so much higher from going from right to left. It's going to do this until this side starts to decrease in particles and this side starts to increase in particles. And when that happens, that's going to occur, and eventually it's going to reach equilibrium, and the rates of going back and forth are the same. Okay. Okay, so what does that look like in terms of chemistry? Well, let's take a look at this problem here. Um, this one. Okay. Consider the following reaction. CO2 plus water will make H2CO3, carbonic acid, Now you notice the double arrow, meaning it can go back and forth. This is actually a reaction that you will see in soda. Carbon dioxide will dissolve in water to make carbonic acid, and it doesn't stay carbonic acid though. I mean, if you've had soda before, you know that that CO2 will come out of the solution and evolve out of the soda. So it's continually going back and forth, and there's some rate. Now, what we want to know is how these rates are going to change when we disturb it. Okay, and there are different ways we can disturb it. So, for example, first of all, let's establish which sides are reactants, which sides are products. These are the reactants, CO2 and H2O, and the product is H2CO3. Okay, so number 11, which way will the reaction go, forwards or backwards, if more product is added? So remember, when we added more, these things are in equilibrium. If we add more to one side, that's basically going to push it the opposite side. So in this case, we're adding more product. That means we're adding more H2CO3. Add more to this side. If we add more carbonic acid, that's going to force the reaction backwards. It's going to force it to go this way because we added more on the right side. So more CO2 and H2O is going to be produced if we somehow add more carbonic acid to this system. Okay. Now, number 12, which way will the reaction go, forwards or backwards, if more H2O is added? So in this case, we're adding more H2O. So we're adding more. Add more water. Well, if we add more water, you're introducing much more particles on the left side. You're giving it a much higher chance of colliding with CO2 to react with CO2. And if you do that, it's going to force the reaction more towards the right and produce more carbonic acid. So this is going to force it forwards. Okay. And the last one, which way will the reaction go, forwards or backwards, if some H2O is removed? So now we're removing H2O. Remove this stuff. So we're removing more particles. That's giving it a lesser chance of reacting with CO2 then, because there's so few particles there to do so. And when that happens, again, like in this picture, if we remove particles on this side, there's gonna be a less likely chance that it will move to the right. More particles on the right will move to the left. So back to the example, if we remove H2O, then that's going to force the reaction backwards, because H2CO3 is going to continue to break apart into CO2 and H2O, and it's going to do that much faster than CO2 and water going back towards H2CO3 because you've removed some of that water. Okay, so you can think of it as kind of like there's a gap there now. You've removed H2O, you've created a gap, and that's just going to force more product to move backwards into the reactant side.